That is already registered there. So there's room for talk and questions, so you can go up there. And yeah, that's it. So without any further delay, I would like to welcome Dr. Vjeran Visnjevic from the University of Tübingen. And he will be talking to us today about assessing the stability of ice shelves in Antarctica. So Vjeran, it's all yours.
Thank you very much. Hello, everyone. My name is Vjeran Visnjevic, and I'm a postdoc in Tübingen in the group of Reinhard Treves. And today I'll be talking about Antarctica, about ice shelves and their stability. But more precisely, I'll be talking about how we can use the stratigraphic record of ice to learn more about the past conditions of ice flow, the atmospheric and boundary and basal conditions of ice flow. And I will try to teach you what people have done using radar stratigraphy measurements and combining them with ice flow modeling and what they have learned about mainly Antarctica from it. And then I will focus on the results of my study, where we look at ice shelves in particular. Maybe it's good to start every Antarctica talk with a global Antarctica velocity map, just to get a sense of what's happening and where things flow. So in Antarctica, the main of accumulation, the ice gets accumulated in the inside, in the interior, and then it flows increasingly with increasing velocity towards the ocean, and there it is stopped, it is buttressed by ice shelves. For that reason, because they are stopping large amounts of ice flowing into the ocean, stability of ice shelves is very important and a crucial part of study of climate change. Today, I will look at trying to understand through their stratigraphy, their composition, what part of the ice gets accumulated directly from the atmosphere, and what part of the ice shelf is from the grounded ice flowing towards the ice shelf. And then in this kind of context, we will discuss what the predictions of climate change of Antarctica have to say about what we can expect for the ice shelves. Before I continue, it's maybe important to emphasize some basic and new terms, and one of them is probably isochrones. And we will talk about isochrones today, and we will talk about how they are used on a global scale and on a regional scale in a short introduction, where I will show you what other people have done in their work. And then we will focus on ice shelves and compare the model stratigraphy with data obtained from radar measurements and what that tells us about the ice shelf. And we will then delineate for all Antarctic ice shelves the difference between local meteoric ice, so ice formed on the shelf directly, and continental meteoric ice, which is ice flowing from the continent into the ice shelf. And in that context, we will kind of discuss and investigate ice shelf stability and sensitivity to projected future changes in mass balance over the continent and over the ice shelf part of Antarctica. It's now important to say how we model isochrones and what they are. So when we model our ice stratigraphy, we solve the age equation, and the important thing in the age equation is two terms. One is that every year an ice particle becomes 1 year older. That's quite simple but very important. And the ice particles are advected with the velocity field around the ice shelf or grounded ice. This is very important because basically to model the age stratigraphy, the age field of ice, we just need a good velocity field. And this is one of the main things that we will be using, and I will explain how we derive it. Most radar obtained internal layers are isochronal. They're isochrones. They are surfaces of the same age. So as you can see in the upper right corner, we have a radar image of an ice rise. And if I zoomed in a lot more, you would see quite nice layers, visible layers from radar. And we interpret each of these layers as a layer of the same age. And then when we model this process, we get images like this. And here in color coded below in the bottom left is the age of the ice, and you can see that the shapes kind of correspond to what we see in reality. Layers are a combination. They provide a spatial and temporal representation of the evolution of the ice mass, and they help us to disentangle some of the influences of some of the processes in this evolution of the ice mass, and I will get to this in quite a bit of detail very soon. So before I start talking about ice shelves, I just want to show you 2, 3, 4 studies that have used isochrones and modeling, and just show you how it works and what kind of results people have gotten. In the case of Greenland, we have a good coverage of radar transects. So in the left figure, you can see color-coded by the ages of the campaigns that Greenland is completely covered by radar transects, and we have a good firm grip on the radar stratigraphy over Greenland. And when we combine that with the position of ice cores, from which we can connect the layers to ice cores and then get dates from these ice cores, that allows us to map very finely the spatial distribution of the ages, and not just the layers, but of the ages across Greenland. And one of the recent study done by Bourne and Robinson in 2021, here I show you a cross section of, let me see if I can make it this highlighter, no, pointer. Yes, so here cross section, you can see how Bourne and Robinson have modeled the Greenland and its stratigraphy. So here you can see the surface in black, the real data is in black, the surface and the bed, and then we have in black dashed lines, we have observed isochrones, and then in color, in green and blue, we have modeled the isochrones depending on the scenario. And that allows us then to check how well our climate forcings work, how well we know have constraints on the climate evolution over Greenland, but also how well we know certain ice dynamical properties and parametrizations, and we can then check how well that works. In the case of Antarctica, Antarctica is much larger than Greenland, so we don't have that many radar transects. We have a lot more than this, but I'm showing you here a study by Sutter et al. In 2021, where they did a 200,000 year run, and they modeled the stratigraphy of all of Antarctica, and then compared it with the transects they have connected with ice cores. I will zoom in the one particular in Dome C, so you can see how these results look like. And they show results for 2 transects, DCY77A and DCX57A. And I will, this is quite a bit of a large figure, but I'll try to quickly break it down just so you get a sense of what's happening. So in the upper right, the circles represent the direction and the magnitude of velocity. The color-coded values on the bottom are geothermal flux and basal melting. So in gray dots and black line at the bottom is the differences between radar imaged bottom and the one used in the model. In the top, blue and black is the blue is the observation surface elevation, and black is the modeled one. And then here, what we are really interested in is the 2 sets for each transect. It's the red lines represent the data. They represent the picked radar lines, so isochrones, from 38,000 years ago to 160,000 years old. They are connected to the ice cores, so they are dated. And in both transects, you can see that there are areas where the fit is extremely good. It's really well, it's really correct. And then there are areas where there are smaller offsets and area where there are larger offsets. And that's all good because we learn a lot from a data model of misfits and discrepancies. So one of the reasons for this can be simply our lack of constraints in the past changes of climate or bad conditions or ice dynamics features, and it could be just not well resolved climate forcings on this scale. So there is a lot of reasons that we can investigate why our models differ from observations, but using this kind of extra information besides surface and besides bedrock and ice thickness allows us really to kind of disconnect certain influences, and we will get to see that on ice shelves very soon. So on a smaller scale in our group, we have done a lot of work on ice rises, especially the PhD work of Clara Henry. So here I'm showing you the Roi Baudouin Ice Shelf, and within it the Derval ice rise, where we have very good constraints on the stratigraphy of this ice rise, because during campaigns we have quite a bit of radar transects through all, as you can see in the bottom left figure. And Clara then tries to model with high precision this ice rise, and she uses LMI ice for this. So I didn't mention, but the other large scale simulations are usually done by using some sort of simplification of ice flow, but on a smaller scale we can investigate this in high precision with a full Stokes set of equations. So we solve the full set of equations describing the flow. And she uses LMI ice to model the stratigraphy of this ice rise. And here you can see the differences between her fit in black dotted lines and the observations across the FF transect. Observations are in black, and you can see that the trends are very well matched, and even the depths of certain lines and certain ages. And this Clara is using this isochronal record to help her constrain the ice dynamical properties of ice rises, such as the flow exponents in the Glen's flow law or enhancement factors in the deformation, and that tells us how and under what regimes this ice rise flows. Secondly, her results in what I'm showing you here are very interesting, because they also allow us to get a better sense of how old is the deepest ice in the ice rise. So if we would decide to drill a core in this ice rise, we know that the bottom ice is around 8,000 years old. So this is the record we could obtain from it. And these studies then allow us, on a smaller scale, allow us to not only get a sense of global changes over Antarctica and Greenland, like we saw in previous studies, but over more local and regional areas, which is something that we always want to know with higher precision, because it's important for our modeling and for the understanding of the system as a whole. So another thing in our group, we have, besides forward modeling, we have done some inversions. And this is the PhD work of Guy Moss, who infers ice shelf mass balances from isochrones and ice shelf geometry. So one of the things important to know is that we can get from flux divergence. So if we know velocity and thickness on one side and velocity and thickness on the other side, we can calculate the total mass balance. And then if we have knowledge about one of them, either the basal melt or surface accumulation, we can obtain the other one. But what the guy is showing in his PhD work, that by using internal stratigraphy, we can decouple this total mass balance directly from isochrones and geometry into accumulation and basal melt. And in the right side of the figure, you can see in the top right corner, it's a dot that represents the surface accumulation. And at the bottom right corner, it's B dot that represents the basal melt. And you can see in the ice shelf, depending on the different spatial forcings of these two fields, we get a different structure. We get the same geometry, but we get different internal stratigraphy. So we use this internal stratigraphy to then disentangle between the influences of surface accumulation and ocean melt or basal melt. So there is high value in isochrones, and we can learn a lot from it, and they can help us add additional information in situations where we cannot decouple certain forcings. Guy furthermore applies this to the external ice shelf in the Droning Maudland. Here you can see the ice shelf and its velocity field, and in red is the radar transect obtained by our colleagues Reinhard Devs, Inka Koch, Reza El-Sadi, and Falko Jarshavsky in the last 2 years. In 2 campaigns, they collected over 100 kilometers of radar data along the flow line, and Guy uses it to invert for a surface accumulation in basal melt. Here I show you only his results for only part of the transect. And here in A and in B dot, you can see the constraint in red, the constraint posterior distribution, so inverted surface accumulation and basal melt. And in blue, you can see the prior, so the distribution he started with. And here in the middle figure, you can see, middle right finger, you can see that his age, he has the age of this layer, and also he very well reproduces the radar layer observed. So these kind of methods will allow us to learn a lot more about local conditions of ice shelves and what we do. He uses this machine learning method called SPI together with the machine learning cluster in Tübingen. And not only does he manage to retrieve the surface accumulation and basal melt, but also the uncertainties that follow it. So this is all just a short overview of both global and regional studies using isotope modeling and internal stratigraphy. And now I want to talk about what I do and want to show you my results. And I will talk about ice shelves now, and I will first describe ice shelves. So ice shelf evolution and its integrity is influenced by surface accumulation, basal melting, and ice dynamics. And we see the signals of all of these processes imprinted in the ice shelf geometry and its stratigraphy. And that is its importance for us in this study. How I will look at this is, you have to keep in mind, I'm a modeler, so my reality is quite simple, and there'll be a lot of sketches in this talk because we don't go out to the field much, we stay behind our computers. So I look at an ice shelf. So it starts at the grounding line where grounded ice becomes floating ice. And we assume plug flow over an ice shelf. Plug flow means nothing else that besides that the horizontal velocity does not change with depth. And then I will, for the rest of the talk, I will look at an ice shelf as, in a way, a two-body problem. I will look at ice formed directly on the shelf itself, and then I will look at the volume of ice that is advected from the grounded continent to the ice shelf. And I will call this LMI for locally accumulated ice here in blue, and in gray, continental meteoric ice, the ice advected from the continent. I will try not to use many abbreviations in this talk, but these are the two I will stick with. And I'll try to just remind you what they mean as we go. How do I do this? So I said we needed to solve the age equation. And to solve the age equation, we need velocities. Because we have plug flow and we assume that there is no change of horizontal velocities with depth, we can set our boundary conditions. And then from observations, from satellite, we can plug in simply horizontal velocities. And then we can calculate the vertical velocity using a simple empirical formula derived by Devs et al. In 2020, where vertical velocity is a function of surface mass balance, basal mass balance, ice thickness, and strain rates. And when we have all the velocities, we can solve the velocity fields, and then we can map out what part of the shelf is locally accumulated and what part is continental advected to the ice shelf. Now, you might ask, why is this important? Not just as a stratigraphy, but why these two ice bodies? Well, one of the main reasons is that the future projections for surface mass balance over Antarctica differ over grounded ice and over ice shelves. So in both situations, it is projected that the temperature will rise, but over both ice shelves and grounded ice, but they will have very different effects over grounded ice and over ice shelves. So over grounded ice, the increase in temperature will result in increase in surface mass balance, increasing accumulation, and even further increasing the advection of that ice towards the ice shelves. While over ice shelves, this increase in temperature will lead to the reduction of surface mass balance and to higher melt. And you can see this, so in the left, bottom left figure, it's the grounded ice projections for Antarctica for 3 scenarios. The thick lines are the change in SMB projected, and the dashed lines are change in temperature. So we have an increase in temperature, an increase in SMB, and over ice shelves, the dashed lines, we have an increase in temperature, but a reduction in surface mass balance. So these 2 ice bodies will ice shelves that are dominated by one or the other source of meteoric ice will react differently to these changes, to these projected changes. And for that, we are interested in mapping what part of the shelf, how much of the shelf is dominated by local accumulated ice. Let's first talk shortly about a model setup. These are all 3D simulations. I use LMI ice, so this is an ice solver that solves the full set of equations, but I will not do that. I will use our empirical relations because it drastically reduces computation time. I use the A solver published by Martin and Goodmanson in 2012. For all of the ice shelves that I show you, the resolution is between 500 meters and 1 kilometer, depending on the size of the shelf, and 25 vertical layers, and simulation time is between 500 and 1,000 years. It's situated depending on the shelf. We assume a steady state geometry. We here on the upper right corner, I show you again the Roi Baudouin Ice Shelf and its grounding line. We use geometry, so surface thickness and bottom from bed machine. So from published observations, surface velocities as well, SMB from Lennart's and from ACMO, and BMB over all of Antarctica is from Adusumili. So we use all the observations that we can to calculate and the surface velocities to calculate the vertical one, and then create a full 3D H field, and then we continue with its analysis. So before I go to all of the ice shelves, I want to talk more about Roi Baudouin, because I want to show you how these results look on one ice shelf, and if we understand how we interpret the results and what we can see, then it's going to be easier to expand this to all of them. So let's focus here first on the dashed lines. Let's focus first on the D1 and D2 transects. And here I show you the H field for both of them. So because of ice shelves, we do not have a connection to the ice core, and we have a very messy signal at the grounding line. I do not model the stratigraphy in the ice flowing in from the continent, but I focus on the stratigraphy of the locally accumulated ice, and that's also in this ice shelf. This is the part of the shelf where we have obtained radar data. What I want to show you here is just that both east and west of the shelf have very different structures, and that's something that's worth keeping in mind. So both the spatial the layers themselves are different, and they go, the LMI is higher on one side and lower on the other one. We see this even better if we look at the C1, C2, C3 cross sections, where we can see that depending on the side of the ice shelf, we have very different flow regimes, and that's very interesting and something that we should keep in mind. And in order for us to now understand how much can we believe our results, I will show you comparison of our results along the A and B transects where we have radar data. And before I do that, I want to show you how the radar data looks like. So this is kind of magic for me because I'm a modeler and I don't do a lot of radar stuff or a lot of radar imaging, but this is what a radar image looks like. And honestly, I wouldn't not know where to look at layers, but when you zoom in, you can see that here they are. And let me just show you the structure of this image. So we have picked layer, we can pick the surface, we can pick the ice space, and then in between we have internal radar reflections, and they are not real features, and we have to be careful not to interpret them as such. So now we have picked layers, we know the surface, we know the base, and let's compare our results with observations. So first I will focus on the a long flow AA transect. And here you can see colored in age. So in color is from blue to red is the modeled isochrones, so the lines of the same age, and in black we have the observed radar horizons, so observed isochrones. And as you can see, as we move away from the grounding line, our fit is better and better. And we have offsets, small scale offsets, and we have larger scale offsets closer to the grounding line. And that can be for different reasons. The small scale offsets can be due to simply coarseness of our forcings, of our velocity field, of our surface accumulation, of our basal melt, and simply the discrepancies. Our model is 1 kilometer while the observations are 6 meters. So there is a large discrepancy. There is variability that a model cannot catch. While on the left-hand side here, there is a larger discrepancy that is probably due to there is a strong winds in this part near the grounding line, and that results in a negative surface mass balance that we do not have in our surface mass balance field that we use for this model. So that leads in the overestimation of depth of our isochrones, and we know that there is strong katabatic winds in this area because of blue ice fields showing up here, which means that there is constant winds that constantly blow away winds and then ice, and then they remove mass. And because we don't have this in our model, it could be that this is the main source of this discrepancy. If we look at the BB across flow transect, we can see that here the differences are mainly on the smaller scale, which is due to simply inadequate, like too coarse forcings that we used in our model, because our velocities and our surface accumulation is on 5 kilometers, our velocities are 500 kilometers, so it's we cannot reproduce the high scale variability we obtain from radar. But all in all, this is quite a good fit, and this kind of encouraged us that we can then, in this way, model ice shelf stratigraphy. We can use this simplified velocity field that is very quick to calculate, and then that allows us to expand this approach. Before we go on and look at all of the ice shelves, I want to show you a result where we now map the percentage of the locally accumulated ice within the whole ice shelf. And here you can see that the first thing we see, there is a spatial variability. There are high differences between the western and the eastern part of the shelf. Let me just first stop here and the color coding. So the red represents the locally accumulated ice, the local meteoric ice, and that will be so for the end of the talk. And blue represents the continental ice, the ice advected from the continent, and this will remain in blue. We have high differences, and one of the main things they follow is the velocity field. This, the left side of the ice shelf is fed by an ice stream with high velocity, and that ice then there's a higher flux, and a lot more of that ice reaches much further in the ice shelf. And we can then see that there is differences in responses in the future changes in SMB with this ice shelf. For the part that is completely blue, we expect nothing will happen to it because it will continue to be self-feeding, self-sustaining from the continent, while the part that is a large in part fed by locally accumulated ice will experience more thinning due to this reduction of projected reduction of surface mass balance in the future. So then we have done this for all of the ice shelves. I have model stratigraphy of local meteoric ice, and I have then mapped the percentage of it within a shelf itself, and then we can map this for all of them. And this is something I will show you right now. So here it is. We can now see in zones the percentage of locally accumulated ice in red compared to the ice advected from the continent, and how much of that is ice shelf composition in the ice shelf composition. What we can first see is that the big ice shelves, so the Rhone, the Ross, the Aimery, are mainly fed from the continent, and we believe that these large-scale changes in ice shelf surface mass balance will not affect them in this sense, not at the scale that we expect for the other ones. So what we really I want to focus here in this talk is the Antarctic Peninsula, the ice shelf and the ice shelves in the Bellinghausen Sea and the Amundsen Sea, where they are mainly dominated by the local meteoric ice and which is projected to reduce. But not only that, I here confront this image with a thinning rate, the rate of thickness change over Antarctica, studied by Paolo et al. In 2015. And there we can see that the areas that are dominated by locally accumulated ice already experienced thinning. So here we see the Larsen Ice Shelf and Bellinghausen Sea and the Amundsen Sea. And we see the shelves that are dominated by LMI are actually gaining mass. The ice shelves dominated by continental ice are actually gaining mass. So this is already the situation. So the ice shelves that are dominated by local accumulation is already are thinning, and this can, and they will continue to thin even more. This can be even better seen in study by Andersen et al. This year, where they show the area growth and area retreat in kilometer squares per decade, and you can see that the ice shelves that are dominated by locally accumulated ice are already losing area, and they are losing their thickness, while the big ice shelves and the ones dominated by continental ice are not. Furthermore, if we look at the projected ocean temperatures, we can see that not only there will be expected reduction in surface accumulation in these areas of high LMI, but also increase in ocean temperature. So that will overall reduce the thickness of ice, making them more unstable. So all in all, what we can see comparing these studies and the results I just showed you is that ice shelves dominated by local accumulated ice already experienced thinning and area reduction, and they are and there it is also projected that they will continue to lose more. So here, just to remind you again of the spatial variability and changes. So here, if you look at the scenarios, largest reduction of SMB is really in the area of the peninsula, the Larsen Ice Shelf, and these two seas, and that just becomes more and more clear in higher warming scenarios. Let's now zoom in and look at these areas in more detail. So first, on the left-hand side, we have here Larsen Ice Shelf. That is, here we have two ice rises using as spinning points, and as we can see, a large part of the shelf and the whole system in the Antarctic Peninsula is dominated by locally accumulated ice. And in the other two parts that I spoke about, the Amundsen Sea, you can see that ice shelves are mainly dominated, these plates here, but the other ice shelves mainly dominated by ice locally accumulated atmospheric ice, and then so LMI, and that really puts them in danger, but also corresponds with these projections. And then if we kind of focus on a larger area that is mainly dominated by a continental ice, here I show you the Joning Maudland, and here in the middle you have the Fimbulisian ice shelf fed by a strong ice stream, and as you can see, there is a whole flow of ice from the continent, a lot of continental ice all the way to the pinning point, and we believe that such dominating area of continental ice will continue to feed the ice shelf, and that the stability of this shelf in the context of local LMI and CMI is not in danger, and that they will be this ice shelf will be self-sustaining from the ice directly from the continent. What I to finish this talk slowly, I want to show you how these results correspond when I plot them against the results of Furst et al. In 2016, who mapped, the authors mapped the buttressing strength of Antarctica's ice shelves. And in, I don't know, I think this is dark yellow or something, in dark yellow, let's say, you can see high buttressing strength. So these areas are important for containing the flow and important for ice shelf stability. And then in light blue, or you have areas with weak buttressing, and these are the passive ice areas. These areas do not help with containing the ice coming from the continent. So in order to kind of visually, we can see that there are some overlaps and there are some common things in these two fields, but I very quickly yesterday, I plotted a density plot, a scatter plot, and then a density plot of these two results just to get a sense of how things correspond. And here, this is, you can see this is the latest figure, so it's less nice than the other ones, but just to quickly show you, so we have our buttressing results from Furst from 0 to 1, and then we have our LMI from 0 to 1. And we see for large areas here that are meaningful. The one is areas with high buttressing and low LMI, which means that they have high CMI. So these areas are areas of high buttressing and a lot of continental ice. And in these areas, because of the Ross and the Rhone and the Ross and the Emery ice shelf, this is highly represented because a lot of area, these are big ice shelf, and a lot of areas there have a lot of CMI. So the major part of buttressing from ice shelves is the part of ice shelves that is fed by from the continent. And we call this self-sustained ice shelves and self-sustained areas of ice shelves because we believe their volume will continue being fed from the Antarctic ice from the continent. The second part we have is high LMI and low buttressing. These are the edge areas in the low buttressing zone, so in the passive ice zones, and they depend highly on LMI because they are mainly consisted of LMI, but because they are in the passive zones, they are less important for the buttressing strength of the shelves, and the disintegration of these areas will not lead to large structural instabilities of the ice shelves. So we call this part the passive areas. And then the upper right corner, we have ice shelf parts that are high in LMI and high in buttressing. And this is the most vulnerable part of ice shelves because these are areas that are completely dependent on local accumulation, on local surface mass balance, but they are still, these are still areas of high buttressing, so high importance for the buttressing strengths of the ice shelf. So their disintegration and weakening of these parts will lead to potential weaknesses in the structural stability of ice shelves. So we say this part is vulnerable to atmospheric changes. So we can map these kind of zones from looking, first we map our LMI percentages across the Antarctica, and then for all of the shelves, we can do these kind of density plots, and we can then see which parts of the shelf belong to these zones. This is work I have yet to do, but this is now the next thing. And then we can actually map out exact locations where our results show there is highest danger of structural stability, for the structural stability of shelves because of high buttressing strength area and because that area is fed in by the local accumulation. And just to conclude, by combining radar, isochrones, and iceflow modeling, we can improve our model calibrations, we can help constrain past changes in atmospheric forcings and ice dynamics, as I have shown you in the studies of Greenland and Antarctica and ice rises and ice shelf inversions. We modeled isochrone layers and calculated the percentage of local meteoric ice for all of Antarctica ice shelves, as I have shown you, and we map zones dominated by local meteoric ice and identify the ones that are susceptible to projected changes in SMB and BMB. And the model stratigraphy for all of Antarctica ice shelves can be used as prior information in future inference studies. So this could be very useful because we always need an initial guess and a prior for our inversion studies. And now we have basically we have a collection of modeled stratigraphy for LMI for all of the ice shelves around Antarctica, and that can be quite useful for future work. And thank you very much. That is all for me.
Thank you, Vjeran, for a really interesting talk. And now we are open for questions. So anyone who has questions can type in their questions and we can read them out for you. And yeah, so by the time we start getting a few questions, I can start. And I think my question is more connected to two parts. There's this first part where you showed that there was a model data comparison, and that was for a smaller area, it seemed. And there was agreement, but there was also like a disagreement between some of the parts. And then you had the projections for a lot of shelves around Antarctica on the east and the west. And that was really interesting. Is that modeled as well as comparison with data, the final projections that you show over there? Is that...
So I'm sorry, when you say the projections, do you mean these two graphs showing over ground and ice, the SMB will increase, or the map, or the big map?
Oh, the map of your, like the thinning on like the eastern part and, you know.
Yes, my map is modeled, so the LMI percentages, but then the maps, I compare them with the thinning and the area increase and reduction. They are from observations. And then the projected increase in SMB over grounded ice and reduction of SMB over ice shelves, that's a modeling results. So it's a combination. Some of the thinning ones, there was from observations. The area change, that's from observations. The climate projections in the future, that was from models, and buttressing was also from modeling.
Okay, so when you go from, these small scale projections to like much bigger, I mean, what kind of an error or uncertainty do you expect in your?
Well, that is one of the things that we can now do with in 2D. In the beginning, I showed the work of Guy Morse, who does an inversion method on a transect, and that can be you can quantify uncertainties there because it's quick to calculate a long flow and stratigraphy of a long flow ice shelf in 2D. The problem becomes when we switch to 3D because the area is just huge. So let's say that the Ross ice shelf, the bigger one, is the size of Spain, so it's really large areas. Even the smaller ones are really the size of countries. Like the Roi Baudouin that I was showing is the size of Moldova. It's still a big country, so it's very hard to do a proper uncertainty quantification because there are errors from observations, but then there are the models. Let's say for the Roi Baudouin ice shelf that I was showing in the beginning, the one where I compared with observations, it takes 22 hours for one run to get the stratigraphy, and that is with the simplification of velocities. So it's very complicated to get uncertainties or to get a sense of them because the forward models are so computationally expensive at the time. But we are trying to tackle this. We're trying to now use inversion methods in 2D, 3D on grounded ice as well, and then slowly build up from small areas to larger zones. But it's still very, very, what we can do is we can do a set of parameter change, like we can do a parameter sensitivity analysis, different parameters with different ranges, and get some sense of how these things change, but a full uncertainty analysis is still too expensive computationally.
Okay, yeah, thank you.
Okay, great. So we have a question in the chat from Francisco asking, are there any particular areas you've identified the causes of the discrepancies between model and observations of radar layer stratigraphy, isochrones, or is it too complex to find out the causes?
It depends, of course. So there is many sources of uncertainty and error in our modeling, of course. What I would try to say as a good thing is that, let's say, the discrepancy in Roi Baudouin that I was showing a long flow, I think that is really due to we have a negative surface mass balance at the grounding line that is not in our model, in the field that we were using the forcing, because it's simply to course the field. And then if we don't have a removal of ice in that area, we cannot be even in that area, we cannot fit the observed isochrones. I think Sutter in his paper mentions that there could be parameterization of basal melting that are less correct as we move closer to the coastal parts of Antarctica, and then this could be the main sources of uncertainty. But we also have to be very careful with assigning these things, because let's say in ice shelves now, I have assumed steady state, right? So there is no change in geometry, but also no change in the transient forcings. And this is, of course, an assumption, and it works well because we can quite well reconstruct the layers later on. But we should always keep in mind that we have made quite a bit of assumptions, that we do not know the transient changes of our velocity field, of our surface accumulations well. And I would say that that my results in the Roi Baudouin show that we need that there is a negative surface mass balance near the grounding line, but there could also be different reasons we could explain that.
Okay, thank you. I prefer to write because someone is hitting with a hammer at home, and then
oh, I know this. Yes, yes. We've all had these Zoom meetings, yes, when the building is working.
Okay,
thank you for your question.
So I might have a more general question, but please, anybody in the audience who has a slightly more technical question, again, this is not my expertise, but thank you again for an excellent talk. It's really cool to hear. And certainly from somebody who, this isn't my background, the introduction section was particularly helpful. So thank you very much for kind of laying that groundwork. That was really helpful. So again, this might be completely off the topic, but I'm just wondering what you think the role of sea ice might be in a lot of your assumptions, and when you're thinking about, you know, how these ice shelves, the dynamics of them, and potentially thinking about sea ice and whether it has any role to play then in potentially affecting how much change there might be, certainly looking into the future and some of your projections towards the end about what we think might happen. I don't know. Do you have any thoughts about that?
Yes. So I cannot, from my results, I cannot comment on that because of the assumption of steady state, and not we don't change the geometry. So the idea is we can kind of just quantify certain metrics and certain percentages, and then discuss it and see what could happen to this in regards with other changes. So I do not model sea ice in this sense, but the importance of sea ice is there for sure, and not only for the salinity of the water around, and the temperature and the conditions of the currents, and now it all comes back to more slight oceanography, and it's something we need to measure and model a lot more, and people are doing great work now on this, and they're following sea ice with machine learning methods and trying to model its behavior and where it ends up. In this regard, from my results, I haven't looked at it in that sense, and I cannot comment on like what effect it would have, but it's a topic of many studies at the moment. Like this EGU had a lot of sea ice talks, and people are doing a lot of good work on that topic.
Okay. Great. Thank you very much. Sorry, again, I realized it might have been a little bit left field. It was just when you were talking about some of the stuff, I just thought
No, absolutely.
Yeah. Okay, thank you.
Okay, then we don't seem to have any more questions in the chat, and we are almost close to an hour. So if there are no more questions from the audience, then maybe we wrap up this session for today. And yeah, thank you all for attending Landscape Live, and we will see you all next week. And yeah, so bye everyone.
Thank you everyone. Have a nice day. Bye-bye.